Hello everyone, this is Arnav Vaidya and I am going to explain a research paper titled Survey of Dynamic Programming Algorithm by Mr. Yunong Zhang. Imagine you are packing a bag for a trip and a bag has limited number of slots. You can fill the bag with the most weight or with the most value. Looking at either one is not the most optimal solution. That's why we compare them and reach to a solution. This is one of the core concepts of dynamic programming. Here, we are going to look at what the research paper glosses over in a presentation form. We are going to go over the core concepts such as optimal substructure, recurrence relations, overlapping subproblems. We are going to look at one of the classic cases of dynamic programming, the 0-1 knapsack and its variants. We are going to look over the applications of dynamic programming in the real world and and some optimization strategies which we use to reduce the time complexity and computational time of these algorithms. Now let's begin with the introduction to the same. Dynamic programming is a very powerful tool which we use to, to sort do optimization. It is a bottom-up method which divides the problem into many subproblems and exploits optimal substructural routines. Dynamic programming is used to find optimization, sequence alignment, and path search. These problems usually take lots of time, computational time, but with dynamic programming, we can reduce it to polynomial time. Here are the basic principles of dynamic programming. These are like the axioms of dynamic programming on which it stands on. Here, on the first step, we find an optimal substructure to exploit. The optimal solution is derived from the subproblems and the aggregate of it. We get a recurrence relation where we summon the function repeatedly to solve the subproblems. And lastly, we find overlapping subproblems. These overlapping subproblems get us a full picture and don't solve already repeated subproblems and we store the results in a dynamic programming table, which we will see later. Here is the time complexity and space complexity analysis. Time complexity analysis clearly shows that most of the dynamic programming problems are solved in polynomial time. Here, sometimes the growth can be exponential and and to improve on it, we use strategies such as pruning and approximation algorithms. In space complexity, we see you generally dynamic programming problems require 2D tables or a matrix to store subproblem solutions. However, in higher states and dimensions, we use state compression to save our space. Now, let's see the knapsack problem. Knapsack problem is a classic problem. It it just has it just selects maximum total value without exceeding a knapsack limit. It includes three key elements. First, the capacity of the knapsack. Second, the collection of the items. And lastly, selection restriction. Here, 0, 1 is for one each, multiple is for limited copies, and unbounded for unlimited copies. So, here is the strategy to fill in the DP table. First, we initialize the boundaries. Secondly, we define a subproblem we can call recursively. And, and thirdly, we apply transitions to fill the table row by row using state equations. And to find the optimal solution globally, we use a backtrack. In the state of the state transition equation is the heart of the solution. If item I fits the knapsack, we pick the maximum value it can offer. If it does not, We do not take the solution. The result we have stored in a matrix, which is n is the number of elements, and weight. Now we are going to see the knapsack problem with the DP table. Here capacity is 10 and we have 4 items. First we initialize it by putting everything as 0 and we start filling the table. Here we look at each passes and each pass tries to solve the problem. However, by the fourth pass, we reach an optimal solution. At the bottom left, you can see uh, the capacity has been maxed and the maximum value has been reached. Therefore, we have selected the items 1, 2, and 4 and backtrack the solution from the matrix 4 and 10. Now, we are going to see a coding solution for the same. First, we are going to initialize the DP table. Then, then we are going to solve the backtracking problem. Here, the first for loop looks for the item in the range of n, 0, and -1. According to our recurrence relation, if the item fits and has the maximum weight, and per unit value, we pick it and we backtrack the solution to look for any redundancies and faults. Thus, this is the gist of the back knapsacking algorithm. Now, let's change the problem a bit. Multiple knapsack. Multiple knapsack, we have along with the weight, the value, we have number of copies of the same. Therefore, for each item I, we choose k copies. Therefore, here we pick the two copies of item 1 and one copy of item 3 for the optimal solution. Now, this is the code solution for the same. Here, we use a pruning strategy such as for when we run an inner loop for every k tries for item I, the brake system prunes in improbable states early. Thus, we avoid unnecessary iterations once our weight is achieved. Now, let's look over real life applications for dynamic programming. Dynamic programming algorithms power real tools such as speech recognition, DNA sequence alignment, and and companies like AlphaFold leverage it to analyze amino acid sequences to infer 3D protein structures, advancing disease natures and drug design. Now, despite limitations in time and space complexity, we can optimize the algorithms such as memoized search. We can use top-down DP that caches computed subproblem results, avoiding redundant recursion and significantly reducing computation time. We can do state compression, where high-dimensional states are compressed into one-dimensional or two-dimensional representation using bit operations. We can use a multi-stage dynamic programming approach, which decomposes multi-stage decision problems into sequential subproblems. Now, to conclude, can find went over the foundations, the classic cases such as the knapsack problem. We implemented it via Python and we looked over its IRL applications. Now, for the future, we can see as computing power and algorithmic advances, DP will play a greater role across multiple disciplines. Therefore, to conclude, dynamic programming solves problems efficiently and to practical problems and enhances research for new possibilities in computer science and other fields. Thank you.